Hello everyone, welcome to Computer Science 226, lecture number 2. Okay, let's get to the slides. Today we're going to have a very short lecture. It'll be all about overview of computers. That's basically the stuff which we already covered in 190, but it's very important to reiterate that over the courses. So a lot of theoretical information, basically how the computers are built, and that's also the material which you'll be tested on later in this course on quizzes and midterms, final exams. Class updates. If you guys have any issues, please attend tutoring sessions. Please send me an email as well. We would like to help you out. In general, we're going to have quizzes on Thursdays, right? Not today, but starting from next Thursday, and homeworks due on Mondays. So this week, next week on Monday, we're going to have the first homework, okay? Always email me if you have any questions. As I said before, starting from today, what I want you to do, I want you to take notes while you're watching the lecture, and I want you to submit those notes, take a photo and submit them by midnight of today, okay? Let's start. So one of the simple questions I'm usually asking at quizzes or midterms, right? All the exams is what does CPU stand for? What does it do? And how many bits in a byte? What is the difference between high-level language and assembly language and low-level language? So I'll basically go over everything you need to know, all the background. I'll do that very, very quickly, kind of hoping that you remember that from 190, just kind of refreshing your memory. Okay, so hardware and software. Computer systems consist of hardware and software. There are two things. Hardware includes tangible parts of computer systems, everything which you can feel, everything which you can touch, which are motherboard, graphics card, SSD, HD, CPU, right? So like if you disassemble your laptop, so everything you can touch is basically the hardware, right? Software includes programs, which are a set of instructions for the computer to follow, right? And we as software developers, we need to know both sides. But software is more important, of course, than hardware. Most computers nowadays have similar components. They are input devices, keyboard, mouse, output devices, display screen, printer, the audio system, actually. A processor, two kinds of memory, main and auxiliary. So the processor, that's also called CPU, Central Processing Unit, or chip, Pentium processor, right? Intel Pentium, which is not a thing anymore, of course. The processor processes programs instructions, right? It processes only very simple instructions. Hope you remember back in January, we were talking about that, and I said that a processor is only capable of something super simple, like add, subtract, mul, multiply, div, divide, load, meaning that we're going to load something from the memory, store something back to the memory, and usually, like, depending on the architecture, depending on the processor, they would have, let's say, like 30 super simple instructions. Memory. So memory holds programs, data for the computer to process, results of intermediate processing, right? So let's say I'm writing the program which adds two numbers together. So those two numbers will be the data. That thing, when you add them together, that will be the program, right? And the results will be stored somewhere in the memory. There are two kinds of memory, main and auxiliary. So what's main memory? Main memory is RAM, right? RAM stands for random access memory. So working memory used to store the current program, the data, the results of intermediate calculations, usually measured in gigabytes. That's not correct. Gigabytes. For example, 8 gigabytes of RAM, right? RAM is short for random access memory. A byte is a quantity of memory. Like a bit later, we'll be talking about bits, bytes, kilobytes, kilobits. Well, not kilobits, kilobytes, megabytes, gigabytes, terabytes. When we talk about the memory, we generally mean main memory, right? Which is your RAM. And that's a chip, that's the RAM, right? It contains 8 chips. Right, each one of them is, let's say, one gigabyte or 2 gigabytes, and that would make, so if we have 8 chips, that means the entire board would be 16 gigabytes or 8 gigabytes. Auxiliary memory. Auxiliary memory is also called secondary memory. That would include disk drives, CDs, DVDs, flash drives, all that stuff. More or less permanent and non-volatile. So the difference between non-volatile and volatile memory is that non-volatile memory is persistent. If you turn off your computer, right, that memory, the data in that memory is not going to be wiped out. So for example, the data on the hard drive, if you download some kind of computer from some kind of data, some kind of program from the internet and keep it on your SSD, when you turn your computer off, that data is not going to be erased. And that's how secondary memory works. However, with main memory, which is considered to be volatile, that's kind of the opposite. So in the main memory, something is stored there automatically. You don't really know how it's being done, but the operating system handles that. And then when you turn off your computer, the whole thing is wiped out. So it's more or less permanent, usually measured in gigabytes, not 50, right? So it's usually power of 2, but let's say 64 gigabytes. Okay, bits, bytes, and addresses. A bit is a single digit, right? Digit with value either 0 or 1, right? So something either exists or it doesn't exist. It's either yes or no. A byte consists of 8 bits. So 1 kilobyte consists of 1024 bytes. 1 megabyte consists of 1024 kilobytes. 1 gigabyte consists of 1024 megabytes. 1 terabyte consists of 1024 gigabytes. And so on. Each byte in the main memory resides at a numbered location called address. Here's an example, here's the picture. That's called a memory map, right? So basically that's the value of each byte and that's the address of each byte. So it's kind of similar. If I want to write you a letter, if I want to send it to you, I'll have to write there, I don't know, like John Smith, 315 Florence, South Carolina, and then provide the zip code, right? So that's the address of you, right? So if we now translate this example into computers, into RAM, then like over here in this cell, we're gonna write John Smith, and then on the left, we're gonna write 315 Florence, South Carolina, because that's the address. Storing data. Data of all kinds, numbers, letters, strings, characters, audio, video, music, video games, even programs are encoded and stored using zeros and ones. Again, so the computer is basically a bunch of transistors, a huge amount of them, right? And those transistors can only understand zeros and ones. However, those huge amount of zeros and ones are being translated seamlessly. You don't really realize that it's happening into everything you see and hear and play on your computer. When more than a single byte is needed, several adjacent bytes are used. The address of the first byte is the address of the unit of bytes. Files. Large group of bytes in auxiliary memory are called files. Files have names. Files are organized into groups called directories or folders. Okay, and Java programs are stored in files. Program files are copied from auxiliary memory into main memory in order to be run. Zeros and ones, machines with only 2 stable states are easy to make. Okay, so again, historically, back in the 50s and 60s, when the first computers or the first boards were manufactured, so back then they kind of decided that the easiest way to create anything digital would be like create a transistor, and transistor can be either charged or discharged, or capacitor. So a transistor in the mode of capacitor. Capacitor can be either charged, which means it's going to represent 1, or it can be discharged, where it's shorted to the ground. In this case, it's going to be represented 0, right? So again, that's the easiest way to make a digital system, to make a machine, to make a computer. However, it's very difficult to code that way, of course, because again, back in the day, those guys who used to code using zeros and ones, like, so instead of saying system.out.println, they would say 0, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, right? And if, let's say, you want to add 2 numbers together, like 5 and 7, you would have to write, so I remember I was coding in binary, right? That would be like 8 lines of code. Each line of code would be 32 bits, right? So 32 zeros or ones. And of course, it's impossible to read. Like, it's possible, but it's very difficult to do. Yeah. Fortunately, conversion of numbers, letters, strings, characters, audio, video, and program is done automatically, seamlessly. You don't even realize that it's actually happening. A program is a set of instructions for a computer to follow. We use programs almost every day: email, word processor, video games, bank ATMs, all that stuff. Following the instructions is called running or executing the program. So when you hit the run button, you execute the program. Normally, a computer receives two kinds of inputs: the program and the data that's needed by the program. Right. So, for example, if I write the Java program which adds two numbers, 5 and 7, then 5 and 7 would be the data, and the program would be the code I write. The output is the result produced by following the instructions in the system. So here is kind of the illustration of that. You can kind of think that your program is a black box. You put something inside of that black box, right? In this case, the data, like 5 and 7, and that black box spits out something different, 12, which is a sum of two numbers. Okay, operating system is a supervisory program that oversees operation of the computer. The operating system retrieves and starts the program for you. Well-known operating systems are Windows, macOS, Linux, Unix, iOS, Android, Chrome OS, and all different kinds of distributions of Linux. High-level languages are relatively easy to use. So Java is one of them, right? C#, C++, Visual Basic, Python, Ruby on Rails. Unfortunately, computer hardware does not understand high-level languages, and that's why we need compilers, interpreters. Compiler. What's a compiler? Compiler translates a program from high-level language into low-level language the computer can run. You compile a program by running the compiler on the high-level version of the program called source program. Okay, so again, on one hand you have Eclipse where you write system.out.println. On the other hand, you have zeros and ones which CPU is executing. So that translation from printout println into zeros and ones, that's what compiler is doing. A compiler translates a program from a high-level language to a low-level language the computer can run. You compile a program by running the compiler on high-level language, which is called source program. So the code you write in Eclipse, it's called source code or source program. Compilers produce a machine or assembly language program that is called object programs. Compilers, most high-level languages need a different compiler for each type of the computer and for each operating system. So usually that's how it works. Let's say, for example, I'm supervising some team which develops processors for Intel. Okay, and those guys, for example, we decide within a team meeting that, I don't know, 0001 is going to be the code, machine code for addition, for the add command, and then 0010, right? Or let's say 0000 for zeros will be subtraction, and then 0010 will be multiplication. Okay, so that's only our decision. Now the guys at Qualcomm, right, who develop Snapdragon, they say like, hey, like those guys at Intel suck. That's not how it should be, and they decide to go with like 0000 division, then 0001 multiplication, right? So they change the entire thing. Of course, I'm oversimplifying this, but basically, people who develop those processors, they decide themselves what they want to do, what kind of commands they want to create. There is no uniform standard across the manufacturers. That's why if I write the code for Intel processor assembly code, it's not going to be working for Qualcomm, okay, or for any other manufacturer, and that's kind of a problem. And that's why people who wrote compilers, they would have to create a compiler, for example, for C for each one of the processor. And it's possible that, for example, when Intel develops a new processor, the commands, the instruction set is going to be changed from the previous version of the same processor, like Intel Core 7 and Intel Core 9, right, or 5 and 7, right? They do not necessarily need to be the same, right? It's completely up to the manufacturer how they decide to do that. So that's always been an issue. I mean, especially at the very beginning. Now nobody really cares about that. There are a huge amount of ways around. But yeah, anyway, most compilers are very large programs that are expensive to produce, right? And Java kind of solved the problem. They created so-called bytecode. Java compiler does not translate the Java program into assembly language. It translates that into the bytecode. So that bytecode is being run on so-called virtual machine, JVM, Java Virtual Machine. right? Java virtual machine. And then basically what happens is that when I compile my code, I have the object code which I can send to you, right? And you can run that object code on your Java virtual machine on your computer. A bytecode program is easy to translate into machine code language for any particular computer. A program called an interpreter translates each bytecode instruction, executing the resulting machine language instructions on a particular computer before translating the next bytecode instruction. The most Java programs today executed using just-in-time compiler (JIT) compilers, in which bytecode is compiled as needed and stored for later reuse without needing to be recompiled. So there are two commands which you kind of need to know and kind of not. Java C, which means Java compile, and then after you compiled it, you can run it using Java command. Again, when you're using Eclipse, everything is done for you. That's one of the advantages of using Eclipse. You don't really need to understand that much. But if we're doing that without Eclipse, we would have to write the code in, let's say, Notepad, then compile it using Java C command, and then run it using Java command. Portability, again, so why is Java so popular? Why Java became so popular? That was possible because, again, I would compile my code on my computer, send the bytecode to you, and it will still work, which is called portability. Class loader. A Java program typically consists of several pieces called classes, and actually I think in this class we'll finally learn about the classes, what they are. Each class may have a separate author, and it can be compiled separately. A class loader, which is also called linker, automatically connects the classes together. You know that. That's not interesting. Yeah, applications and applet. So there are two kinds of Java programs, applications and applet. Applications are regular programs. It's something like what you guys are doing and meant to be run on your computer. Applets are very, very small applications meant to be sent to another location on the internet and run there. So a person who writes a program is called a programmer. A person who interacts and uses it called a user. A package is a library of classes that have been defined already. Right? Scanner, for example. We need to import that. Arguments, right? So the items inside the parentheses when we create a function is called argument. A variable is something that can store data. An instruction to the computer is called a statement. And the grammatical rules, right? So Java has very strict grammatical rules. Hope you remember that. That's all called a syntax. Okay. So how do you print out? You can say system.out.println. That's how you invoke the method, right? You basically say the method name and then you provide the arguments, and then you all close that with a semicolon, right? Compile in Java, Compile in Java program or class. A Java program consists of one or more classes, most likely one. In 190 we used only one class. In this class I think we'll be using two classes and more, which must be compiled before running the program. You need not compile classes and the company Java, right? System and scanner, right? You don't have to compile those classes. Each class should be in a separate file. The name of the file should be the same as the name of the class. For example, if the name of your class is homework1, then the name of the file needs to be homework1.java. IDE, our Eclipse is called IDE, which stands for Integrated Development Environment, which combines a text editor, commands for compiling and running Java programs. Right. A Java program can involve any number of classes. The class to run will contain the words main, right? I hope you remember that. It's possible that you have a lot of methods, a lot of functions in your code, but only the one which is called main is going to be executed. So from that main, you can call all other functions, but if in that main you're not calling anything, that nothing will be done, right? Hope you guys remember that. Errors, there are three types of errors: syntax, runtime, logic errors. Syntax errors, what does that mean? That means you guys did not, if you run into syntax error, that means you did not follow the rules. For example, you said system instead of system.out.println, you said system dot out and forgot the dot, println, system.out, println. And of course Java will be like, what the hell is that? Not sure what that means, and it's going to tell you that it's a syntax error, sorry. It's not going to correct it for you, it's not going to try to guess, oh, he probably meant .println instead of just println. No, it's just going to throw an error. Grammatical mistakes in the program, compiler catches syntax errors, prints in the message. Runtime error, right? So that usually means that the syntactically everything was good. You put all the semicolons, all the dots, all the colons, everything was cool. However, when it was able to compile the code, but when it was running, it realized that there is a problem. For example, again, if you divide something by 0, if you say like a is equal to 5, b is equal to 0, c is equal to a divided by b, then it may be a runtime error. Really depends on the version of the compiler, but most likely will be runtime error. And logic errors, what does that mean? That means syntactically, no problems, runtime works perfectly, right? So Java did the best it could, it did exactly what you asked for. However, the result is different from what you want it to be, right? So for example, again, if I want to, like in this case, I want to calculate Fahrenheit temperature from Celsius, right? By multiplying by 9/5 and adding 23 instead of 32, right? So again, I basically said temperature times 9/5 plus 23, although I should have done times 9/5 plus 32, right? So Java doesn't really know, it doesn't really understand what you were trying to do, it just executes everything you told it to, and since you told it to add 23, it's going to add 23, not 32, because how would ever Java know that what the purpose of your program is? Okay, cool. We're gonna stop here. I hope it makes sense. Nothing difficult, just repeating the same information. Please submit the notes. Homework will be due on Monday. I'll see you guys on Tuesday. Bye bye.